NASA is on the brink of a transformative breakthrough in space exploration thanks to the successful testing of advanced nuclear propulsion technologies that could significantly reduce the journey time to Mars to just 45 days. This innovative development primarily revolves around two cutting-edge technologies: nuclear thermal propulsion (NTP) and nuclear electric propulsion (NEP). Overview of technologies. 1. Nuclear thermal propulsion (NTP). Recently tested at NASA's Marshall Space Flight Center, NTP utilizes a nuclear reactor to heat a liquid propellant, most likely hydrogen, to create thrust. This technology has the potential to achieve speeds 2 to 3 times faster than conventional chemical rockets, drastically changing the dynamics of space travel. The recent tests have shown that the NTP fuel can withstand extreme temperatures exceeding 2,727 degrees Celsius (4,940 degrees Fahrenheit) in hydrogen environments, closely simulating the conditions of deep space. Scott Forney from General Atomics Electromagnetic Systems (GAMS) highlighted this achievement as a critical milestone for future Mars missions. 2. Nuclear Electric Propulsion (NEP). The SPAR program, supported by SpaceNukes, aims to develop advanced fission reactors specifically designed for use in spacecraft. This technology is expected to enhance performance and efficiency with the potential to reduce travel times to Mars significantly. NEP systems are being designed to evolve from a 100 kilowatts power source to a multi-megawatt capacity, which could cut round-trip journeys from over a year to just a few months, making human exploration of Mars more feasible. Common key points. Faster travel. Both NTP and NEP promise remarkable reductions in transit times to Mars, addressing the critical logistical and safety challenges associated with long-duration space missions. Current chemical propulsion methods typically require about 6 months for a one-way journey, exposing astronauts to cosmic radiation and mechanical failures for prolonged periods. Enhanced safety. Shorter travel durations would significantly minimize radiation exposure and the need for extensive supplies, thus enhancing astronaut safety. This advancement also facilitates better management of risks associated with communication delays and medical emergencies. Collaboration and development. The collaboration between NASA and industry partners such as GAMS and SpaceNukes underscores a collective effort to operationalize these technologies for future Mars missions and beyond. Differences between sources. Focus on technologies. Some sources emphasize the strategic development of NEP and its implications, while others delve into the specifics of NTP testing and its immediate relevance for Mars missions. Testing details. While one source provides in-depth insights into the testing environments and conditions of NTP fuel, another discusses the broader implications of NEP without specific test conditions. Timeline of events. 2018, SpaceNukes successfully designed and tested the 1 kilowatt kilopower reactor for NASA, laying the groundwork for nuclear propulsion technologies. 2025, NASA conducted successful tests of NTP fuel at the Marshall Space Flight Center, confirming its survivability under extreme conditions, marking a pivotal moment for deep space exploration. Future prospects. Ongoing research and testing will continue to refine these technologies, with NASA actively pursuing collaborations to integrate these systems into upcoming missions, including potential Mars missions in the 2030s. Implications for space exploration. The advancements in nuclear propulsion technologies signal a significant leap forward in human space exploration capabilities. By promising faster, safer, and more efficient journeys to Mars and beyond, these technologies may redefine humanity's presence in space. As they mature, they could facilitate ambitious missions to the outer planets and the establishment of sustainable habitats on the Moon and Mars. Conclusion. In summary, NASA's developments in nuclear propulsion technologies, particularly NTP and NEP, represent a transformative shift in the potential for human space exploration. With the promise of reducing travel times to Mars to just 45 days, these innovations not only enhance the feasibility of long-term missions but also address critical safety and logistical challenges. As NASA continues its collaboration with industry partners, the dream of interplanetary travel becomes increasingly attainable, paving the way for a new era in space exploration. NASA's testing of advanced nuclear propulsion technologies, particularly nuclear thermal propulsion (NTP) and nuclear electric propulsion (NEP), represents a significant leap forward in the quest for efficient human travel to Mars, potentially reducing trip durations to just 45 days. This development has profound implications for space exploration, fundamentally altering how missions to the Red Planet and beyond may be conducted. Counterintuitive information. 1. Reduced travel times versus safety concerns. While one might assume that faster travel times inherently increase risks due to the intensity of the journey, the opposite is true in this context. The shorter duration of a trip to Mars decreases astronauts' exposure to cosmic radiation and other dangers associated with prolonged space travel. This reduction in time could lead to safer missions, which counters the intuitive notion that longer missions would be inherently safer due to more time for contingencies. 2. Nuclear technologies as green solutions. Nuclear propulsion technologies often evoke concerns regarding safety and environmental impacts. However, the advancements in NTP and NEP could be viewed as environmentally friendly alternatives to traditional chemical propulsion. These nuclear methods, by being more efficient and requiring less propellant for the same thrust, could significantly reduce the carbon footprint associated with space launches and operations. 3. Public perception of nuclear power. There is a common perception that nuclear technology is inherently dangerous. However, NASA's progress in nuclear propulsion shows that when designed and tested under stringent safety protocols, nuclear systems can be reliable and safe for space missions. This may challenge the widespread fear and skepticism surrounding nuclear energy, suggesting that public understanding could evolve as these technologies are validated through successful missions. 4. Collaboration with private industry. The collaboration between NASA and private companies like General Atomics and SpaceNukes could be seen as an unexpected shift in how space exploration is conducted. Traditionally, government agencies have been seen as the primary drivers of space technology development. However, the involvement of private industry indicates a trend toward public-private partnerships that could enhance innovation and efficiency in space exploration. 5. Underestimated time for development. While the promising results from tests suggest a rapid progression towards operational nuclear propulsion systems, the reality of integrating such technology into actual missions might take longer than anticipated. Although plans are in place for Mars missions in the 2030s, the complexities of developing, testing, and ensuring the safety of nuclear systems mean that the timeline could be more extended than the optimistic projections suggest. 6. Potential for broader applications. The implications of nuclear propulsion extend beyond just missions to Mars. The technology could enable more ambitious exploratory missions to outer planets, which many might not anticipate. The ability to travel faster with greater payload capacity could open new avenues for discovery, including the establishment of sustainable human outposts on the Moon and Mars, which often feel like distant aspirations rather than imminent possibilities. 7. Economic implications. The development of nuclear propulsion systems might initially seem cost-prohibitive given the complexity and safety measures required. However, the long-term economic benefits of reduced travel times, increased mission efficiency, and potential for commercial applications could lead to a net positive impact on space exploration budgets. This economic argument counters the immediate perception that nuclear options are necessarily more expensive. 8. Technological leapfrogging. The advancements in nuclear propulsion may lead to a situation where next-generation space missions could leapfrog current capabilities entirely. Instead of incremental improvements, we might see a radical transformation in space travel that redefines mission parameters, timelines, and capabilities, challenging the view that progress in aerospace technology always follows a linear path. By recognizing these counterintuitive aspects of NASA's nuclear propulsion advancements, we can better appreciate the complexities and potential of future human space exploration endeavors. This technology not only promises to revolutionize travel to Mars but may also reshape our understanding of safety, efficiency, and the role of nuclear power in the cosmos. NASA's advancements in nuclear propulsion technologies, specifically nuclear thermal propulsion (NTP) and nuclear electric propulsion (NEP), represent a significant leap in the future of space exploration, particularly for human missions to Mars. While many of the benefits of these technologies, such as faster travel times and enhanced safety, are highlighted in the report, there are several critical aspects that are often overlooked yet hold significant implications for the future of human space travel. 1. Technological synergy and evolution. One of the most crucial but understated elements in the report is the potential for synergistic development between NTP and NEP technologies. While both propulsion systems can significantly reduce travel time to Mars, their combined use could yield even greater advantages. NTP can provide rapid transit for the initial journey to Mars, while NEP could be utilized for in-space maneuvers, orbital adjustments, or even missions to the outer planets due to its ability to operate continuously over long periods. This synergy could redefine mission architectures, allowing for more complex and ambitious exploration plans. For instance, NEP could enable spacecraft to travel not just to Mars but to other celestial bodies, expanding humanity's reach in the solar system. The strategic planning of using both systems could enhance mission flexibility, enabling astronauts to conduct diverse scientific research and exploration tasks without the limitations imposed by current propulsion technologies. 2. Long-term sustainability and infrastructure development. Another significant aspect often overlooked is how nuclear propulsion technologies could support the development of sustainable human habitats beyond Earth. The report emphasizes the reduction of travel time and associated risks, but it fails to address how these technologies could facilitate the establishment of permanent bases on the Moon and Mars. Nuclear propulsion systems can allow for more frequent and larger missions, supporting the transportation of not only crew but also substantial cargo necessary for building infrastructure such as habitats, laboratories, and life support systems. This capability is vital for establishing long-term human presence on Mars, which is a prerequisite for extensive exploration and potential colonization. Furthermore, the availability of nuclear propulsion could lead to the development of a sustainable energy infrastructure on Mars, utilizing local resources to produce fuel for return missions or for powering habitats. This could reduce dependence on Earth for resupply missions, making human exploration of Mars more feasible and economically viable. 3. Psychological and social implications of shorter travel times. The potential for significantly reduced travel times also has profound psychological implications for astronauts. Extended missions, particularly those lasting over 6 months, pose challenges not only in terms of physical health but also mental well-being. The isolation, confinement, and stress associated with long-duration space travel can lead to various psychological issues, including anxiety and depression. By cutting the journey time to Mars down to just 45 days, the mental strain on astronauts could be considerably lessened. Shorter missions would allow astronauts to engage in more direct and frequent communication with Earth, alleviating feelings of isolation. The report touches on communication delays but fails to elaborate on how enhanced communication capabilities can foster better mental health, camaraderie, and mission success. 4. International collaboration and geopolitical implications. The collaboration between NASA and private industry partners such as GAMS and SpaceNukes is highlighted, but the broader geopolitical implications of these advancements are often overlooked. The development of nuclear propulsion technologies could catalyze international cooperation in space exploration, particularly as multiple nations look to establish a presence on Mars. As countries race to explore Mars and other celestial bodies, the potential for collaborative missions, shared technology, and joint research initiatives could lead to a more unified approach to space exploration. This collaboration could also mitigate the risks of space militarization and promote a peaceful exploration ethos, fostering global partnerships that transcend earthly conflicts. 5. Environmental and ethical considerations. The report does not delve into the environmental and ethical considerations surrounding nuclear propulsion technologies. While the benefits of reduced travel times and enhanced safety are clear, the implications of using nuclear reactors in space must also be addressed. Concerns regarding potential accidents, radioactive waste, and the long-term impact on celestial bodies need to be part of the discourse. Moreover, as humanity expands its presence in space, ethical considerations regarding planetary protection and the preservation of extraterrestrial environments are paramount. The deployment of nuclear propulsion technologies should be accompanied by stringent safety protocols and environmental assessments to ensure that exploration does not lead to contamination or irreversible damage to other planets. Conclusion. While the advancements in nuclear propulsion technologies by NASA represent a transformative shift in human space exploration capabilities, it is essential to recognize the broader implications that extend beyond mere travel times and safety. The potential for synergistic development, sustainable infrastructure, psychological benefits, international collaboration, and ethical considerations are all critical components that deserve attention. As humanity stands on the brink of a new era in space exploration, a holistic approach to these advancements will ensure that we not only reach new worlds but do so responsibly and sustainably. 1. Technological breakthroughs in propulsion. NASA's development of nuclear thermal propulsion (NTP) and nuclear electric propulsion (NEP) represents a significant leap in space travel technology. NTP utilizes a nuclear reactor to heat hydrogen, achieving speeds that are 2 to 3 times faster than traditional chemical rockets. This advancement allows for a potential Mars journey of just 45 days, drastically reducing travel time and addressing critical safety concerns related to long-duration space missions. 2. Safety and logistical enhancements. The reduction in travel time offered by NTP and NEP significantly mitigates risks associated with cosmic radiation exposure, equipment malfunctions, and limited medical support. A shorter journey means astronauts face less time in a high-risk environment, allowing for improved management of emergencies and reducing the need for extensive supplies. This enhancement makes human missions to Mars not only more feasible but also significantly safer. 3. Collaborative efforts and future prospects. NASA's partnerships with organizations such as General Atomics, Electromagnetic Systems (GAMS), and SpaceNukes emphasize the collaborative nature of advancing nuclear propulsion technologies. Continuous research and development, along with the integration of these technologies into upcoming missions, including potential Mars expeditions in the 2030s, illustrate a strategic commitment to enhancing human presence in space. 4. Broader implications for space exploration. The successful testing of NTP fuel and the development of NEP systems signal a transformative change not only for Mars missions but also for future deep space exploration. With the capability for faster travel and increased payload capacity, these technologies could facilitate ambitious missions to outer planets and support sustainable human habitats on the Moon and Mars, ultimately redefining humanity's capabilities in space exploration. Here are 3 famous historical cases that resonate with the theme of revolutionary technological advancements in space exploration, similar to NASA's developments in nuclear propulsion technologies. 1. Apollo program and the Saturn V rocket. The Apollo program, initiated by NASA in the 1960s, aimed to land humans on the Moon and bring them safely back to Earth. The Saturn V rocket, a pivotal component of this program, was the most powerful rocket ever successfully flown. It achieved the unprecedented feat of carrying astronauts to the Moon within a matter of days, showcasing the incredible capabilities of advanced propulsion technology. The program culminated in the historic Apollo 11 mission in 1969, when Neil Armstrong and Buzz Aldrin became the first humans to walk on the lunar surface. This achievement not only demonstrated the potential of rocket technology but also sparked global interest in space exploration and science. 2. Space Shuttle Program. The Space Shuttle program, which operated from 1981 to 2011, revolutionized human spaceflight by providing a reusable spacecraft capable of carrying astronauts and cargo to low Earth orbit. The shuttle's ability to launch, land, and be refurbished for multiple missions significantly reduced the cost of access to space and enabled a wide range of scientific research, satellite deployment, and construction of the International Space Station ISS. Innovations in solid rocket boosters' main engines and heat shield technology played a key role in the shuttle's success and paved the way for future space missions. The program exemplified how advancements in propulsion and spacecraft design can transform human capabilities in space exploration. 3. Voyager program. Launched in 1977, the Voyager program consisted of two spacecraft, Voyager 1 and Voyager 2, designed to explore the outer planets of our solar system. Utilizing gravity assists, these spacecraft executed a series of complex maneuvers that allowed them to visit Jupiter, Saturn, Uranus, and Neptune, providing invaluable data about these distant worlds. The success of the Voyager missions was made possible through innovative propulsion techniques and the strategic use of planetary alignments to conserve fuel and maximize speed. Voyager 1 has since become the first human-made object to enter interstellar space, demonstrating the far-reaching possibilities of space exploration and the effectiveness of advanced propulsion technology in achieving ambitious scientific goals. NASA's recent advancements in nuclear propulsion technology are set to redefine the future of human space exploration, particularly with ambitions to send astronauts to Mars in just 45 days. This radical shift is primarily attributed to two innovative propulsion systems: Nuclear Thermal Propulsion (NTP) and Nuclear Electric Propulsion (NEP). These technologies promise not only to shorten travel times but also to enhance safety and efficiency for deep space missions. Future predictions for nuclear propulsion technologies. 1. Accelerated Mars missions in the 2030s. By the 2030s, NASA and its industry partners are expected to have fully operational NTP and NEP systems capable of supporting manned missions to Mars. The technology is forecasted to reduce the travel time to Mars significantly, from the current 6 months to around 45 days. This rapid transit will alleviate many logistical and safety issues tied to long-duration space travel, such as astronaut health risks from cosmic radiation and equipment malfunctions. 2. Increased mission frequency and scope. The introduction of nuclear propulsion will likely allow for more frequent Mars missions and the potential for longer duration stays on the Martian surface. With reduced travel times, astronauts can spend more time conducting research and exploration rather than being in transit. This could facilitate the establishment of permanent bases on Mars, enabling sustained human presence and research. 3. Expanded exploration beyond Mars. The capabilities offered by nuclear propulsion systems will not be limited to Mars. Future missions may target the outer planets such as Jupiter and Saturn and their moons, which are of significant interest for astrobiology and resource exploration. The efficiency of NTP and NEP systems could enable missions to these distant targets previously deemed too time-consuming and resource-intensive with traditional propulsion methods. 4. Development of sustainable habitats. As human missions to Mars become more feasible with nuclear propulsion, plans for constructing sustainable habitats will progress. Technologies developed for NTP and NEP could be adapted for use in creating energy systems that support life on Mars, such as power generation and resource utilization, e.g., extracting water from the Martian soil. This would be a critical step toward establishing a self-sustaining human presence on Mars. 5. Commercial opportunities. The advancements in nuclear propulsion will likely open doors to commercial ventures in space exploration. Private companies may leverage these technologies for satellite deployment, space tourism, and even asteroid mining. The potential for rapid transit could attract investment and innovation, leading to a new era of commercial space activities. 6. International collaboration. As nuclear propulsion technologies mature, there will be an increased emphasis on international collaboration in space exploration. Countries around the world may partner on Mars missions and beyond, sharing resources, knowledge, and technological advancements. This could lead to a unified global effort in space exploration, fostering peaceful cooperation among nations. 7. Technological innovations and spin-offs. The research and development associated with nuclear propulsion are likely to yield new technologies with applications beyond space travel. Innovations in materials science, radiation shielding, and power systems could find their way into other industries, enhancing technological capabilities on Earth. This cross-pollination of ideas could benefit sectors such as energy, transportation, and medicine. 8. Regulatory and ethical considerations. The deployment of nuclear propulsion technologies will necessitate robust regulatory frameworks to ensure safety and environmental protection. As these systems operate in space, considerations around nuclear safety, waste management, and international treaties will need to be addressed. Ethical discussions regarding the use of nuclear technology in space will also become more prominent. Conclusion. NASA's groundbreaking work in nuclear propulsion signifies a transformative era for human space exploration. With the potential to reduce travel times to Mars and enhance mission safety, NTP and NEP technologies promise to reshape our approach to interplanetary travel. As we look toward the future, the implications of these advancements extend far beyond Mars, opening new frontiers for humanity in the cosmos. The successful integration of these systems into space missions could lead to a new chapter in our exploration of the universe, making once unimaginable missions a reality.